Wood is a natural material, and one of its most important characteristics is its interaction with moisture. The amount of water present inside wood, known as the moisture content or MC, has a huge impact on its strength, stiffness and dimensional stability. From 0% moisture content when the wood is completely dry, to past the fiber saturation point, when cell cavities start to fill up with water, changes in moisture content directly affect how wood behaves in structures and products. In this video, we'll explore how moisture influences wood, what happens at different moisture levels, and how mechanical properties shift with every change in moisture content. Moisture content is defined as the ratio between the mass of water in the wood and the often dry mass of the wood, expressed as a percentage. This ratio is calculated using the formula that is visible on your screen right now, where MV is the mass of wood at current moisture, and M_dry is the often dry mass. The often dry mass of wood is achieved after drying the wood in 103 degrees Celsius for 24 hours. As wood absorbs or releases moisture, it passes through several key thresholds that define its physical and mechanical behavior. These moisture content levels mark important transitions from often dry to standard indoor situations and eventually to full fiber saturation. Let's walk through the most critical points along this scale. At 0% moisture content, the wood is often dry. From 8% up to 20% moisture content, changes in mechanical properties because of moisture content are most noticeable. Around 8% to 12% moisture content, we reach the equilibrium moisture content or EMC typically found in indoor environments. 12% is the target moisture content for manufacturing, delivering and construction. 13% is the average moisture content during summer. 16% is often the maximum moisture content at delivery. 17% is the average moisture content during winter. And 18% is the maximum moisture content before enclosure. At 27% to 33%, we hit the fiber saturation point for most European softwoods. From this level, the cell walls are fully saturated, but cell cavities remain empty. At around 33% moisture content, or once the fiber saturation point has been hit, cell cavities start filling up with free water. Between kiln-dried conditions, around 8% of moisture content, and the start of the fiber saturation point, which is around 27% of moisture content, wood swells or shrinks as water molecules bind to or detach from the cellulose strands in the cell walls, specifically the hydroxyl groups. This dimensional movement is one of the biggest challenges when using wood in construction and products such as cross-laminated timber. For every percentage point change in moisture content, wood undergoes the following dimensional changes: 0.01% longitudinal, 0.15% radial, and 0.30% tangential. The reason the radial and tangential changes are so much larger than the longitudinal ones is because wood fibers are aligned mostly along the grain. Imagine a bundle of spaghetti. If you get it wet, the noodles don't really grow longer, but they do get fatter and press against each other. In the same way, wood hardly changes lengthwise, but across the grain it swells much more noticeably. As the moisture content of wood decreases to below the fiber saturation point, strength and stiffness increase linearly. Conversely, as the moisture content rises, these properties weaken. For every 1% change in moisture content between 8% and 20%, the following mechanical properties change. Compression strength, parallel to the fiber direction, changes by 5%. Compression strength perpendicular to the fiber direction changes 5%. Bending strength parallel to the fiber direction changes 4%. Tension strength perpendicular to the fiber direction changes 2%. Shear strength parallel to the fiber direction changes 3%. And the modulus of elasticity parallel to the fiber direction changes by 1.5%. This shows that even small moisture variations can have significant effects on wood's performance. Moisture content is a critical factor in determining wood strength, stiffness, and dimensional stability. Below fiber saturation, wood swells, shrinks, and to some degree even changes mechanically with every shift in moisture content. Above it, dimensional changes stop, but the wood remains weaker compared to its dry state. Understanding these effects allows engineers, architects, and woodworkers to better design, build, and preserve wooden structures. This video and the infographic produced were largely based on publications from Swedish Wood. Take a look at their publications for more information about the influence of moisture on wood and cross-laminated timber in general. And to download the infographic that is on your screen right now, head on over to our Patreon page, linked in the description. Stay informed, stay inspired. TimberTalk.